We're going to be looking at electrostatics, and in order to start with electrostatics, we want to look at the electric force. So we're going to turn our attention to the electric force. Which is the force between objects with charge. So if you think back to gravitational force, and that's the F big G. This is the force between objects with mass. The electric force is the force between objects with charge. Electrostatics is the study of electric charge at rest. I can't spell today. Let's try this again. Electric charge at rest. So if you remember back to, I think it was with Newton's first and third laws, we looked at objects that were moving either at constant speed or at rest. Something that was in static equilibrium was something that was at rest. So electrostatics, that static just means it's at rest. As opposed to current electricity, which we will get to, where the charges are moving. So electrical charge. Electric charge is a fundamental property of matter. So it means that it's just part of what it is. So electric charge is the fundamental property of matter, and there's two types of charging. You should know this from hopefully a previous science class. You've got positive. This pen is not writing well today. Stylus. And negative. So the positive charge comes from the protons, the negative charge comes from electrons. An object with an excess of electrons is negative. An object with too few electrons, so too many protons, is positive. And an object with the same number of electrons and protons is neutral. And this should all be review. Like charges repel, opposite charges attract. Again, this should be review. So negative likes positive, negative hates negative, and vice versa. So looking at the elementary charges, protons are going to carry the smallest positive charge. And protons and uncharged neutrons generally reside in an atom's nucleus. Again, this should all be review. Protons are held in the nucleus by something called the strong force. And we're not going to really get into what the strong force is, just know that it's a force similar to, not similar, but in the same category as maybe gravity or the electric force. It's just a fundamental force of nature. The smallest negative charge is the charge on the electron. And in normal atoms, electrons are going to orbit the nucleus. The electric force is too small of spaces. The electric force between electrons and protons supplies the centripetal force to keep the electrons in the atom. So in other words, this Fe for electric will be equal to the centripetal force for electrons. The charges carried by the proton and electron are equal in size. So proton has the smallest amount of positive charge, electron has the smallest amount of negative charge. Those charges are equal to each other. But the mass of a proton is about 200 times the mass of the electron. So what is charge? The unit of charge is the Coulomb. And 1 Coulomb is equal to the charge of 6.24 times 10 to the 18th electrons. And the symbol for Coulomb is a C. Charge is conserved. So because charge is conserved, electric charges move. I cannot write the word electric today. Electric charges move from one place to another. No case of the net creation of destruction of electric charge has ever been observed. So in other words, no energy is conserved, energy can't be created or destroyed. Same idea with charge. So charge cannot be created or destroyed, it's just going to move. In solids, only electrons move. In liquids, gases, or plasmas, both positive and negative ions are free to move. So solids are more rigid, that's why only the electrons are able to move. Liquids, gases, plasmas have more freedom for the particles inside of them. Okay, now looking at electric forces. The electrical force between two charges depends on two things: the size of the charge, so more charge means more force, and the distance between the charges. More distance means less force. So the electrical forces between two charges is directly, let's make this up. Proportional to each charge and inversely proportional to the square of the distance between the charges. Which brings us to Coulombs Law. And I think you're going to find this equation looks very familiar. Fe equals K Q1 Q2 over R squared. I'm going to put a side note in parentheses why I think this looks familiar. Remember, F big G equals G M1 M2 over R squared. So that was the force of gravitational attraction. That was the force between two things that have mass. The electric force is the force between two things that have charge. So what do each of these represent? Fe is the electric force. K is a constant. K equals 9 times 10 to the 9th newtons meters squared per coulomb squared. Store that number in your calculator as K. R squared is the distance between the charges. And the Q1 and Q2 are each charge. So this equation works exactly like the force of gravitational attraction. It's known as Coulombs Law, and it tells you the amount of electric force between any two charges. So it's an inverse square law because of the fact that the farther away the charges are, the less electric force. So just think the closer together, the more attraction or repelling they're going to have. The farther apart, then the less. And it's directly related to the charge. The larger the charge, the more force you're going to have. I'm going to do 2 examples with Coulomb's law, and then we'll get into practicing tomorrow. A negative charge of -2 times 10 to the -4th coulombs and a positive charge of 8 times 10 to the -4th coulombs are separated by 0.30 meters. What is the force between the two charges? So these diagrams are all going to look exactly the same in terms of what you need to show. Obviously, it's nothing with motion because these are not moving, they're just there. It's a static charge at rest. What you do want to show are the two charges, what they are. So we have a negative charge and a positive charge. I'm going to call this charge 1 and this charge 2. The only other thing you really need to show in these diagrams is the direction of the electric force. So Newton's third law tells us that the force between the two charges is going to be equal but opposite. So in other words, the amount of charge on 1 is equal to the amount of charge on 2. It's just going to be pointing in opposite directions. Because these are opposite charges, they're going to attract. So that means the positive charge is going to pull the negative charge towards it, and the negative charge is going to pull the positive charge towards it. So this is the electric force. And they're separated by 0.30 meters. So our given information, doesn't matter what you call Q1 and what you call Q2. So Q1 is equal to negative 2 times 10 to the negative 4th coulombs. Q2 is equal to 8 times 10 to the negative 4th coulombs. And the distance between them is equal to 0.30 meters. And we're looking for the electric force. We're looking for the magnitude of the force. So even though it doesn't explicitly say that, since you're looking for the amount of force between the two charges, one's positive, one's negative, whatever number you get, you're just going to take the magnitude of. We're going to use Coulombs law. Fe equals K Q1 Q2 over R squared. Just putting all the numbers in. I don't write out K, just like I never wrote out big G, because it's a number I store in my calculator as the letter K. So that's that 9 times 10 to the 9th times Q1, negative 2 times 10 to the negative 4th coulombs. Q2, 8 times 10 to the negative 4th coulombs over, everyone makes this mistake sometime, forgetting to square, so 0.3 meters squared. This is going to come out to negative 16,000 newtons. And again, we're only caring about the magnitude of the force, so the electric force equals 16,000 newtons. It had two sig figs, so nothing to round here. I'm going to do one more example just using Coulomb's law, and then we'll do practice in class tomorrow. A negative charge of negative 6 times 10 to the negative 6 coulombs exerts an attractive force of 65 newtons on a second charge that is 0.05 meters away. What is the magnitude of the second charge? So again, simple diagrams. You have a negative charge. It's exerting an attractive force, so that means your other charge has to be positive. We'll call that 1 and that 2. You want to show the direction of the forces, and they're separated by 0.05 meters. Our given information, Q1 is negative 6 times 10 to the negative 6 coulombs. The electric force is 65 newtons, and the distance is 0.050 meters. And we are looking for Q2. So Fe equals K Q1 Q2 over R squared. Just rearranging to isolate for Q2, we get Fe R squared over K Q1 equals Q2. So we have everything, just putting the numbers in. My Fe is 65 newtons times R squared, 0.05 meters squared, over K times negative 6 times 10 to the negative 6 coulombs equals Q2. Putting the numbers in, it's going to come out as negative, but it's asking for the magnitude of the second charge. I could have left out this negative here, that would have been fine. Really what the positive and negative is telling me is the direction of these forces, and that'll come more into play when we add in a third charge. So for now, if I make this the magnitude of that charge, this is just the magnitude of whatever that charge was. This will come out to positive because, again, it is asking for just the magnitude. So this comes out to 3.009, keeps on going, times 10 to the negative 6 coulombs for Q2, 2 sig figs. So Q2 is approximately 3.0 times 10 to the negative 6 coulombs. And again, the negatives get iffy. You don't have to necessarily include them when it's asking for amount. They will be more important for the direction of these forces, so right versus left, when we get into adding a third charge. So that's it for today. We'll do practice tomorrow, and then we will start adding a third charge to see how that works out.